So in this case, in the second scenario, delta P is the same, and suddenly now, let's say it takes 0.2 seconds instead of 0.02. Even more, it'd probably take like, if you did this, like it's like a full second, literally, from start to finish. So we can go even more extreme and say, let's make believe this is a 2-second time period, not 0.02 or 0.2. Suddenly, I'm dividing by 2 instead of 0.02. This right here is 100 times more than this. 100 times more. So the force you feel will be 1/100th of what you felt earlier. 100 times smaller than what you felt previously. Again, if the time period of the collision goes up by a factor of 5, the force goes down by a factor of 5. If the time period increases or doubles, the force halves. Think about that logically. So the force and the time period how are they related? As one goes up, the other goes down. What's the word for that, Nick?
Inversely proportional.
Inversely or indirectly proportional. Very good. So force and time are indirectly related with the impulse momentum theory. Now, first of all, questions on that statement, on that idea that we've gone through, because I'm going to continue with the momentum impulse theory now. I think I have enough power. I'm going to disconnect for a sec so I can move. Any questions on idea? Let's continue to analyze this momentum impulse theory a little bit more. So, let's look at it and let's dissect it piece by piece. If I ask you on the test tomorrow, if I ask you to find the impulse acting, what variables do you need? If I ask you to find the impulse acting, what variables do you need? F times t. Does everybody agree with Nick that F times t is what our definition of impulse is? Agreed? Is that the only answer? There's another answer. If I don't have F and t, M and V, because the left side of the equation involves M and V, right? Isn't delta P having to do with the change in momentum? And if I don't know the impulse, and I don't know F and I don't know T, but I want the impulse, the change in momentum is equal to the impulse. So instead, I can look at this formula and say, well, this is really momentum final minus momentum initial. And as Paola said, momentum is M and V. So if I have M and the velocity, I can find out the change in momentum, and that will equal the impulse. So this is still change in momentum. And this is still the impulse. Is that clear what I'm getting at here? So I could ask you on the test tomorrow to find the change in momentum and not give you mass and velocity at all. So you would have to find F times T instead, and that would equal the change in momentum. So I could do it backwards. That's what I'm getting at. I could tomorrow say, here's the force, here's the mass, here's the time, find the change in velocity. Well, then I have to see, factor an M out of here. M comes out of both these terms. And I'm left with M times VF minus VI. That's the change in velocity you're looking for. Or maybe tomorrow's test, I say to you, the mass and velocities are given, find the time period. Well, you would need to know the force. If you know the mass and velocities, you need the force also to find the time period. So there are many ways we can look at the momentum impulse theory, and it depends on a problem-to-problem basis. So where do we start? Where do we start always? We start with what's circled in yellow here. We always start with that. And that's what's on your formula sheet. And that's all that's on your formula sheet for momentum impulse theory. The next line, PF minus PI, not on your formula sheet. MVF minus MVI, not on your formula sheet. You need to know that delta means change and progress down the formula in that manner. So go from one to the next and decide which you're going to use. Another interpretation of this could be this, by the way. You could also use momentum impulse theory as M delta V equals Ft. That's another way of representing it. And take a look at how that works. Ready? M is in both terms right here. Factor it out. When I factor M out of both, I'm left with Vf minus Vi. And that's what delta V is. Again, if I factor M out of what looks like it's near that blue font, or that blue writing, take an M out in front, I'm left with Vf minus Vi equals Ft, which becomes what's at the bottom. Vf minus Vi is delta V. That's all I'm doing is replacing this expression with the single term or the single quantity delta V. This example is applicable to airbags in a car. You did it with a problem set of your homework. There's an airbag problem. This is applicable to the gymnast problem, where the gymnast dismounts from like a high height and lands on the ground, and he or she does not land with locked legs. Remember I mentioned if you try it, it hurts? It physically hurts. Try it. You land on locked legs. Lock your knees as you jump and land. Just falling this far hurts. I think it was the other section. Thomas Greer, I think, brought it up. If I'm correct me if I'm wrong. But I think Thomas brought up the fact that there's a specific height at which if you land with locked legs, you will guarantee break your knees. Because all of that force hits your legs in a quick, short time period. In a really short time period. Versus landing, when you land and you go like this on the way down, what am I doing? I'm increasing the time and therefore decreasing the force. Remembering that those are inversely related. I'm going to crush this robot. It's really kind of scary to think about, actually. Yeah, that you're inherently, you don't even know you're doing it, but you grow up this way. You grow up that, like, if you ever jump off the jungle gym, right, when you were a kid and you were doing the, like, monkey bars, remember monkey bars? When you fell off or jumped off at the end, you never landed with locked knees. You just didn't do it. It just doesn't make sense logically. You automatically do this because your body tells you to. It's instinctual. You're obeying the law of momentum impulse theory. That's literally what you're doing.
If that's the case, then why are people told that when they jump off like a high height into water, they're supposed to be like a pencil out? You know what I mean?
Yeah, that's different though. That's not, I mean, you're trying to break the surface tension with one small area. So by your feet hitting the surface and breaking the tension right there, it reduces the amount on the rest of your body. That's the rationale for that. But it doesn't, I'm not looking for these bolts. Yeah? Nope, it's on hand? Okay. So, we have two types of problems right there. We have the general momentum question, P equals mv. And this could be like, which of the four objects has the most momentum? Or it could be the mass doubles and the velocity triples. How does the momentum change? Or it could be, find the velocity of a super ball that's needed. If a bowling ball has this much velocity, this much mass. That's the general momentum problem, the first one. Okay, so that's number one up here, if you want to write them down as the four problems. That's the first type of problem. The second type of problem is the impulse momentum problem. So those are the first two types of problems. The general momentum and the momentum impulse problem. After that, we have two more types of problems here. We have the elastic and the inelastic problem. Those are problems 3 and 4. So let's get into those a little bit. The general theory for this entire section with conservation of momentum is this, right here. Okay? With two variables, we can state the entire theorem. Pi equals Pf. What does that mean? And I don't want the next equation. I'm asking what does it actually mean, Helen? Yeah, so momentum can never be lost nor gained. It can only be transferred. Conserved. Very good. The law of conservation of momentum. Now, this leads us to two scenarios. One is elastic and one is inelastic. Elastic means that we have a scenario where the objects will collide and rebound off of one another. I'm not saying that they're both going to be moving initially. One could be at rest. We did this with the soccer ball. We did this with the billiards ball. When one object is at rest and the other is moving, it'll hit and it might move off. They might both move. One might stop, one might move. It depends on their masses. Remember we did that with the demo lab with the carts. If the masses were identical, okay, and you saw it with I think you saw it also in class with the markers. If the masses are identical and an object slides into it with the same mass, this one will hit, stop, and then this one will go. But if this one is really massive, it'll hit this one, launch it forward, and it'll continue to trail past it slowly. If this one is really massive and this one is not massive, it'll hit this one, it'll rebound slowly, and this one will go very slowly. This will rebound off. So if the masses are different or the same, it changes my type of elastic collision. But they're all elastic in all those cases I just mentioned. They could both be moving toward each other with the same mass. And when they hit, they'll rebound. They could be moving toward each other, one with a big mass moving. They hit, and they might both go like that. But again, they separate after the collision is the key.
It's like the beads when that one hits and then it goes.
Yeah, Newton's cradle.
Yeah, so what if you like lift up both beads on either end and like drop it? What would happen?
Would they hit and just stop versus hit and rebound is your question?
Yeah,
They would most likely hit and rebound. I don't know, it's a really good question. Take both objects at the end.
No, it's like this, and they all have like the thing on it.
That's Newton's cradle,
And then these, you lift them up and you drop them.
Yeah.
Would it rebound?
That's what I'm saying. So if you lift them up to the exact same height and they have the exact same mass and the exact same potential energy to start, they would collide, hit here, and that energy this one has in potential, or kinetic as it at the bottom, would transfer into this one in kinetic. This one's kinetic would transfer into that one's kinetic, and it would probably go over and over again.
All the beads over and over?
Yes. Yeah. I want to see it. I got to think about that one first, but it should. If the beads themselves were malleable and flexible and bendable, and this happened, it would most likely hit and then just stop. Because it would absorb the energy itself.
You need like utopian circumstances, not like the same exact height. Like, say, what?
Utopian?
I don't know, perfect, like non, yeah.
Yeah, it would have to, everything would have to be spot on, and the objects would have to physically be able to be deformed for it to stop. Yeah. All right. So, momentum. We want to recognize that it's conserved here. So we have two possible equations. The first one is when they bounce off each other. So this is the momentum of the first object before the collision. Remember, the equal sign means collision. The equal sign means collision. Momentum of the first object before the collision. Momentum of the second object before the collision. Momentum of the first object after, and the second object after. There are four terms because there are two objects moving initially and two objects moving afterward. Now, this is called elastic. You want to put it on the side. That's the elastic example. Now, the second formula can be written two ways. Can somebody tell me why there are two ways to write the inelastic formula? Very good. So we have the fusion problem and the explosion problem. If they start together or start separate. So let's start with them separate first. So let's say they start separately. So the beginning isn't going to change. They still start separately. So it's the same thing as I started with. But then after the collision occurs now, these two masses stick together and fuse. It means that the masses are added together. And how fast are they moving? Well, they're moving with the same velocity, so I'm simply going to call that VF. I don't have to call it V1F or V2F because they're the same. Both objects are moving together. Again, this is the fusion problem for inelastic. You can call it fusion, you can call it coming together, you can call it the joining of two objects, whatever you want to call it, doesn't matter. I call it the fusion problem. Remember I gave the example where you jumped into a shopping cart. Or in your 7-4 notes, a pellet was fired and embedded itself in a cart, and they moved together as an object. I mentioned in the video something called the ballistic pendulum, something that you won't be tested on mathematically, but you should, get the idea. Right? You fire a bullet, it hits an object, that pendulum rises up. Based on how far that pendulum goes up, you can measure the velocity of the bullet. It's really awesome, actually. That's how you measured muzzle velocity for the longest time. Guns were not measured with radar guns. They didn't exist. So they took an object, they took the gun, they fired it physically into a block of wood. The bullet embedded itself into the wood. The wood would rise up like a pendulum. You would get the potential energy at the top. That would equal the kinetic energy at the bottom. Kinetic energy at the bottom would equal the kinetic energy of the bullet, and use conservation of energy and momentum to get the velocity. It was kind of crazy. It was all physics. I mean, think about Anything is all physics, right, guys? Catapults, medieval times, all that stuff was physics. So that's the fusion problem. The explosion or separation problem that Brandon, I almost said Richard for Richardson, that Brandon mentioned involves starting with a lumped mass and then separating afterward. Okay, starting with a mass together and then separating. So you can call this the explosion problem, or you can call it the separation problem, where two objects physically separate into objects that are different. And this is inelastic. This is inelastic. What's the major difference, besides the fact that they separate or don't separate, of inelastic versus elastic? Like, we know one difference, obviously, is that either they fuse together or separate for an elastic, but elastic, they start separate and end separate. That's one major difference we can see with the formula. What's the other difference? What's the other difference? There's one other major difference that we talked about. Got to know this. How come these objects fuse together? How come they fuse together? How come they fuse together? You look like you want to answer. Answer again. Mathematically, that's true, yeah. But I mean physically, why do they fuse together? I'm saying physically, why do they fuse together?
Because of the loss of energy, so they need energy to fuse together.
Yeah, with energy is the answer. The only way for two objects to stick together is by some sort of energy used. So in the second scenario, with the inelastic explosion or collision, we're going to see that the objects themselves are going to separate or fuse together. So as a result, what we're noticing here is that there's got to be a loss in kinetic energy for inelastic. So for inelastic, delta Ke is going to equal some number. For elastic, they hit each other, they bounce off, they don't deform, we assume no sound occurs. Now, this is not realistic, obviously, I've talked about that. But the concept is that there is no change in kinetic energy at all. You saw this with Lab 8. Okay, with the lab that's due tomorrow, you saw this over and over and over again with the first data table and the second data table. The whole first data table, delta Ke was 0. In the second data table, delta Ke was some number each time. Think about a grenade. How does a grenade explode? How does a grenade explode?
Pull the pin,
Okay,
and
and then what?
it's like a little fuse kind of, when you pull the pin, and then
It waits like 3 seconds.
So how does an explosion work, I guess, is the real question I should ask.
The wall full shell of grenade pushes off. I don't know if that's okay.
It's some kind of chemical. Salt.
There's some sort of chemical, I like the fact that it's a chemical reaction for sure, chemical. It could involve many different things, right? It can involve gases, it can involve metals, non-metals, salts, non-salts, it can involve all these different things. Now, what matters is this. For an explosion, the object physically needs energy for the explosion to occur. So it's some sort of chemical reaction in the bonds between the molecules that are being broken that cause an explosion. And I've talked about the fission bomb as an example. The original fission bomb, also known as a hydrogen bomb, was the breaking apart of a nucleus. And it's all the nuclei breaking apart at once, giving off tons of energy, like terajoules of energy, absurdly large amounts of energy, all at once. That's what a grenade is on a smaller scale. But the idea is that you're going to have a delta Ke, because it has to use up some energy to explode, or it has to use up some energy to combine. Think about the bullet with the ballistic pendulum. I fire a bullet into a wooden block, or I hammer a nail into the wall. What's going to happen is heat is generated. If you've ever taken a nail out of wood before, you take a nail out with the back of a hammer, touch the nail right away, carefully, it's hot. It physically will be hot, because there's friction between the metal of the nail and the wood when you remove the nail. When you embed the nail, or when you shoot a bullet and embed it in a piece of wood or a target, it physically produces heat when it passes through and into the object that wants to embed itself. That heat is delta Ke. When I hit a pool ball, I'm playing billiards now, right? When I hit a pool ball, it is modeled as elastic, but it's not perfectly elastic. On your test, I might use the example of a billiards ball and say it's elastic. Then you say, oh, it's elastic. But in reality, when you hit a pool ball, what do you hear? You hear that clink, right? That clink, sound, energy. It's physically energy lost due to sound. So even though a pool ball hitting another pool ball is considered the best example for elastic that we use a lot of the time, it's not still perfectly elastic. Okay, I mentioned to you that there is an example that is very, very, very close to perfectly elastic. So close that it's actually assumed to be perfectly elastic. Do you remember what I mentioned that was? The Super Bowl is close. Super Bowl is close, but it's not. It's like, what was the percentage, right?
Yeah.
It wasn't 100%. It was like 70% or something. Gas particles in a closed container. If I've got a balloon, and if I infuse, one more second, if I infuse the balloon with nitrogen when it's got air in it, nitrogen and the air molecules are going to mix. The bouncing off is practically elastic. Now, reminder, today office hours are right after dismissal, which is like 1:20. Okay, 1:15 is dismissal, so come by around 1:20. I'll probably be there for like an hour today. Okay, after that I'm not going to be there. So come by for the first hour, please.